And today's plan is to finish conservation of energy, and with another example, then we're going to move on to principle of angular impulse and momentum. That's what we're going to do today. Right. Let's see. Example 28 is a problem with a punch bag. So what is a punch bag? A punch bag is a device. Looks like this. I don't know if you box, but I don't. However, there's dynamics everywhere, including, especially in sports. This is center of gravity somewhere here, and the point, 2 points of the rope connecting or hanging the punch bag to the ceiling is defined as point A on the top and point B at the bottom of the rope. And the dimension-wise, the rope is 1 meter. And the bag first of all, from point B to the center of gravity of the punch bag is 0.3 meters. Of course, if there's no force, and this punch bag along with this rope will just stay static, and there's nothing interesting can happen. So there must be a force. Therefore, we have to introduce a force. The force is applied horizontally at here. Suppose there's a force like this, and the distance from the center of gravity to the location where the force is applied is 0.6 meters. It's like that. Okay, so what are we looking for? We are looking for two things. First of all, with the punch bag, of course, initially hanging vertically like this. And after the application of this force, and this force, of course, is coming from somebody's hand, this punch bag is going to move horizontally for sure because of force equilibrium, right? And now, in the meantime, because this cable cannot take moment, that means at the instant when the force applies to the punch bag, point B will be the center of rotation because the rope, you cannot really use the rope to provide any bending resistance. And that means this punch bag is going to rotate. Therefore, there's going to be an angular motion like this. Would you agree? When the force applies, because point B cannot provide any bending moment, so that means at point B, all the moments must be zero. And therefore, as a result, summation of force, summation of moment will be zero at point B. That means the only way to balance this force, which it is not applied at the center of gravity, is to cause this punch bag to rotate. And that is why this punch bag is going to exhibit an angular acceleration because of the moment equilibrium. In the meantime, because of this angular motion, at the center of gravity, this point, center of gravity, will also exhibit linear acceleration. So there's going to be two linear acceleration components at the center of gravity of this punch bag. If you look at this like this, first of all, there's going to be horizontal component, which is in the x direction, right? At the center of gravity, there must be acceleration, linear acceleration. At the center of gravity, we call it AG. And the x component, we just add another subscript. So we call it AGX. What about the y component? Will there be y component? In theory, yes. Now, where should we define the y component? Should we define the y component going up, or should we define the y component going down? What do you think? Is it up or down? Now, to answer that question is to understand the conditions that we define for the problem. First of all, if we allowed this point, which is the center of gravity of the punch bag, to move downward, that means we allowed this vertical acceleration for going down. If you define the linear acceleration in the downward direction, that means you allowed the punch bag actually to move downward. But that's not possible because we assume that this cable or this rope to be inextensible. Therefore, the only possibility for a linear acceleration in the vertical direction, that only possible direction is going up. So we call this one AG, Y. Now, of course, in the meantime, there's going to be angular motion. In this case, it's angular acceleration of this punch bag. And you are also provided with the radius of gyration of this punch bag, which this value K is provided as 0.4 meters. And the punch bag has a mass of 20 kilograms. So two things we want to know. First of all, what is the angular acceleration of this punch bag? So that's what we want to know. One, find alpha. Secondly, we also want to know that what is the tension, the tensile force within developed in the rope. As we know that there's going to be tensile force, right? So we want to know these two. Now, how do we solve the problem? First of all, we recall that from the conservation of energy or from the force equilibrium, we know that summation of all the forces equals the product of mass times the corresponding linear acceleration component. So if we use Fx, and this summation of Fx equals to m times ax, summation of all the forces in the y direction, summation of Fy equals to m times ay. And of course, for angular motion, summation of all the moments, if we consider only two-dimensional problems, in this case, we only have one direction for the moment, which is out of the plane direction. So that's why we don't put subscript here. In this case, summation of all the moments must be equal to the product of mass moment of inertia times angular acceleration. So this is where we figure out what is the angular acceleration in this motion. Okay. And so from here, let's figure out that what is the value of mass moment of inertia. And in this case, we are provided with the mass, the radius of gyration, because k equals to 0.4 meters. That means the mass moment of inertia is what?